Hello and welcome to this section on networking in Kubernetes. My name is Mumshad Manambath and we are going through the Certified Kubernetes Administrators course. In this section, we focus on the networking concepts. Some networking basics are required to get through this section, such as the basics about setting and checking IP addresses on any given system, knowledge on gateways and routes, knowledge about DNS and configuring DNS servers, etc. While working on this section, as before, we sent out a poll asking about your knowledge in networking. Based on your feedback, we've created some prerequisite lectures around configuring interfaces and IP addresses, configuring gateways and routes, basics of name resolution, DNS configuration on Linux systems, as well as how to get started with one of the DNS solutions, Core DNS. These are short lectures that should give you enough knowledge to go through the remainder of this section. It is also important to know a little bit about network namespaces and how Docker uses network namespaces internally. Again, as always, these are for beginners and are optional lectures, and depending on your knowledge, feel free to go through only those that you think you really need. I would highly recommend the network namespaces and Docker networking lectures. Once we are done with the prerequisite lectures, we start with networking in Kubernetes. Again, I'm going to rearrange the topics a little bit to improve the flow. We start by looking at the cluster networking needs, and then followed by pod networking concepts. We then look at CNI in Kubernetes and how CNI can help solve the pod networking challenges. This is where we pick up from where we left off in the prerequisite lectures around network namespaces. We continue to discuss cluster DNS and how Kubernetes implements DNS internally. We then finish with ingress networking. Again, this is one section that I spent a lot of time on, and I hope you enjoy it. In this series of lectures, we get our networking basics right. We look at basic networking concepts like switching, routing, gateways, etc. We then understand DNS, and then we get a basic introduction to Core DNS. We look at how to configure DNS settings on a Linux system. We then understand basics of network namespaces in Linux. Again, I'm not going to bore you with theories on OSI models or network layers. We're just brushing up enough networking to understand the rest of the section in this course. Now, we don't just go through the concepts, we see how these are configured on our systems, specifically from a Linux perspective. So there are going to be lots of commands. We look at these from a system admin's and the application developer's perspective, and not necessarily from a network engineer's. That way, later on when we discuss these in the context of our course, you know what we are talking about, where to look for information, where things are configured, how to troubleshoot, etc. And of course, as always, if these seem to be too basic for you, if you're already good with networking in Linux, feel free to skip these lectures and go straight to the ones on Kubernetes. So let's get started. So what is a network? We have two computers, A and B, laptops, desktops, VMs on the cloud, wherever. How does system A reach B? We connect them to a switch, and the switch creates a network containing the two systems. To connect them to a switch, we need an interface on each host, physical or virtual, depending on the host. To see the interfaces for the host, we use the IP link command. In this case, we look at the interface named ETH0 that we will be using to connect to the switch. Let's assume it's a network with the address 192.168.1.0. We then assign the systems with IP addresses on the same network. For this, we use the command ipaddr. Once the links are up, and the IP addresses are assigned, the computers can now communicate with each other through the switch. The switch can only enable communication within a network, which means it can receive packets from a host on the network and deliver it to other systems within the same network. Say we have another network containing systems C and D at address 192.168.2.0. The systems have IP address 192.168.2.10 and 2.11 respectively. How does a system in one network reach a system in the other? How does system B with the IP 192.168.1.11 reach system C with the IP 2.10 on the other network? That's where a router comes in. A router helps connect two networks together. It is an intelligent device, so think of it as another server with many network ports. Since it connects to the two separate networks, it gets two IPs assigned, one on each network. In the first network, we assign it an IP address 192.168.1.1, and in the second, we assign it an IP 2.1. Now we have a router connected to the two networks that can enable communication between them. When system B tries to send a packet to system C, how does it know where the router is on the network to send the packet through? The router is just another device on the network. There could be many other such devices. That's where we configure the systems with a gateway or a route. If the network was a room, the gateway is a door to the outside world, to the other networks, or to the internet. The systems need to know where that door is to go through that. To see the existing routing configuration on a system, run the route command. It displays the kernel's routing table. And within that, as you can see, there are no routing configurations as of now. So in this condition, your system B will not be able to reach system C. It can only reach other systems within the same network in the range 192.168.1.0. To configure a gateway on system B to reach the systems on network 2.0, run the IP route add command and specify that you can reach the 192.168.2.0 network through the door or gateway at 192.168.1.1. Running the route command again shows that we have a route added to reach the 192.168.2.0 series network through the router. Now remember, this has to be configured on all the systems. For example, if the system C is to send a packet to system B, then you need to add a route on system C's routing table to access the network at 1.0 through the router configured with the IP address 2.1. Now suppose these systems need access to the internet. Say they need access to Google at 172.217.194.0 network on the internet. So you connect the router to the internet and then add a new route in your routing table to route all traffic to the network 172.217.194 through your router. There are so many different sites on different networks on the internet. Instead of adding a routing table entry for the same router's IP address for each of those networks, you can simply say for any network that you don't know a route to, use this router as the default gateway. This way, any request to any network outside of your existing network goes to this particular router. So in a simple setup like this, all you need is a single routing table entry with the default gateway set to the router's IP address. Remember, instead of the word default, you could also say 0.0.0.0. It means any IP destination. Both of these lines mean the same thing. A 0.0.0.0 entry in the gateway field indicates that you don't need a gateway. For example, in this case for system C, to access any devices in the 192.168.2.0 network, it doesn't need a gateway because it is in its own network. But say you have multiple routers in your network, one for the internet, another for the internal private network, then you will need to have two separate entries for each network. One entry for the internal private network and another entry with the default gateway for all other networks, including public networks. So if you're having issues reaching internet from your systems, this routing table and the default gateway configuration is a good place to start. Let us now look at how we can set up a Linux host as a router. Let's start with a simple setup. I have three hosts A, B, and C. A and B are connected to a network 192.168.1 and B and C to another on 192.168.2. So host B is connected to both the networks using two interfaces 80 and 81. A has IP 192.168.1.5, C has 192.168.2.5, and B has an IP on both the networks 1.6 and 2.6. How do we get A to talk to C? Well, basically, if I try to ping 2.5 from A, it would say network is unreachable. And by now we know why that is. Host A has no idea how to reach a network at 192.168.2. We need to tell host A that the door or gateway to network 2 is through host B. And we do that by adding a routing table entry. We add a route to access network 192.168.2 via the gateway 192.168.1.6. If the packets were to get through to host C will have to send back responses to host A. When host C tries to reach host A at 192.168.1 network, it would face the same issue. So we need to let host C know that it can reach host A through host B, which is acting as a router. So we add a similar entry into host C's routing table. This time we say to reach network 192.168.1.0, talk to host B at 192.168.2.6. When we try to ping now, we no longer get the network unreachable error message. That means our routing entries are right, but we still don't get any response back. By default, in Linux, packets are not forwarded from one interface to the next. For example, packets received on ETH0 on host B are not forwarded to elsewhere through ETH1. This is this way for security reasons. For example, if you had ETH0 connected to your private network and ETH1 to a public network, we don't want anyone from the public network to easily send messages to the private network unless you explicitly allow that. But in this case, since we know that both are private networks and it is safe to enable communication between them, we can allow host B to forward packets from one network to the other. Whether a host can forward packets between interfaces is governed by a setting in this system at file proc sys net IPv4 IP_forward. By default, the value in this file is set to 0, meaning no forward. Set this to 1 and you should see the pings go through. Now remember, simply setting this value does not persist the changes across reboots. For that, you must modify the same value in the etc syscontrol.conf file. So let's take away some key commands from this lecture. These will be handy in the upcoming lectures. IP-link is to list and modify interfaces on the host. IPADDR command is to see the IP addresses assigned to those interfaces. IPADDR add command is used to set IP addresses on the interfaces. Now remember, changes made using these commands are only valid till a restart. If you want to persist these changes, you must set them in the etc network interfaces file. iproute or simply the route command is used to view the routing table, and iproute add command is used to add entries into the routing table. And finally, remember the command to check if IP forwarding is enabled on a host, if you're working with a host configured as a router. Well, that's it for this lecture. In the next lecture, we will discuss about DNS configurations. Hello and welcome to this video. In this video, we get introduced to network namespaces in Linux. Network namespaces are used by containers like Docker to implement network isolation. We'll start with a simple host. As we know already, containers are separated from the underlying host using namespaces. So what are namespaces? If your host was your house, then namespaces are the rooms within the house that you assign to each of your children. The room helps in providing privacy to each child. Each child can only see what's within his or her room. They cannot see what happens outside their room. As far as they're concerned, they're the only person living in the house. However, as a parent, you have visibility into all the rooms in the house, as well as other areas of the house. If you wish, you can establish connectivity between two rooms in the house. When you create a container, you want to make sure that it is isolated, that it does not see any other processes on the host or any other containers. So we create a special room for it on our host using a namespace. As far as the container is concerned, it only sees the processes run by it and thinks that it is on its own host. The underlying host, however, has visibility into all of the processes, including those running inside the containers. This can be seen when you list the processes from within the container. You see a single process with a process ID of 1. When you list the same processes as a root user from the underlying host, you see all the other processes along with the process running inside the container, this time with a different process ID. It's the same process running with different process IDs inside and outside the container. That's how namespaces work. When it comes to networking, our host has its own interfaces that connect to the local area network. Our host has its own routing and ARP tables with information about rest of the network. We want to seal all of those details from the container. When the container is created, we create a network namespace for it. That way, it has no visibility to any network-related information on the host. Within its namespace, the container can have its own virtual interfaces, routing, and ARP tables. The container has its own interface. To create a new network namespace on a Linux host, run the ipnetns add command. In this case, we create two network namespaces. To list the network namespaces, run the ipnetns command. To list the interfaces on my host, I run the iplink command. I see that my host has the loopback interface and the eth0 interface. Now, how do we view the same within the network namespace that we created? How do we run the same command within the red or blue namespace? Prefix the command with the command ipnetns-exec followed by the namespace name, which is red. Now, the iplink command will be executed inside the red namespace. Another way to do it is to add the -n option to the original iplink command. Both of these are the same. The second one is simpler. But remember, this only works if you intend to run the IP command inside the namespace. As you can see, it only lists the loopback interface. You cannot see the eth0 interface on the host. So with namespaces, we have successfully prevented the container from seeing the host's interface. The same is true with the ARP table. If you run the ARP command on the host, you see a list of entries. But if you run it inside the container, you see no entries. And the same for routing table. Now, as of now, these network namespaces have no network connectivity. They have no interfaces of their own, and they cannot see the underlying host's network. Let's first look at establishing connectivity between the namespaces themselves. Just like how we would connect two physical machines together using a cable to an Ethernet interface on each machine, you can connect two namespaces together using a virtual Ethernet pair or a virtual cable. It's often referred to as a pipe, but I like to call it a virtual cable with two interfaces on either ends. To create the cable, run the iplink add command with a type set to veth and specify the two ends veth red and veth blue. The next step is to attach each interface to the appropriate namespace. Use the command iplink set veth red netns red to do that. Similarly, attach the blue interface to the blue namespace. We can then assign IP addresses to each of these namespaces. We will use the usual IP-ADDR command to assign the IP address, but within each namespace. We will assign the red namespace an IP 192.168.15.1. We then assign the blue namespace an IP 192.168.15.2. We then bring up the interface using the IP link setup command for each device within the respective namespaces. The links are up, and the namespaces can now reach each other. Try a ping from the red namespace to reach the IP of the blue. If you look at the ARP table on the red namespace, you see it's identified its blue neighbor at 192.168.15.2 with a MAC address. Similarly, if you list the ARP table on the blue namespace, you see it's identified its red neighbor. If you compare this with the ARP table of the host, you see that the host's ARP table has no idea about this new namespaces we have created, and no idea about the interfaces we created in them. Now that worked when you had just 2 namespaces. What do you do when you have more of them? How do you enable all of them to communicate with each other? Just like in the physical world, you create a virtual network inside your host. To create a network, you need a switch. So to create a virtual network, you need a virtual switch. So you create a virtual switch within our host and connect the namespaces to it. But how do you create a virtual switch within a host? There are multiple solutions available, such as the native solution called as Linux Bridge and the Open vSwitch, etc. In this example, we will use the Linux Bridge option. To create an internal bridge network, we add a new interface to the host using the IP link add command with the type set to bridge. We will name it vnet0. As far as our host is concerned, it is just another interface, just like the eth0 interface. It appears in the output of the IP link command along with the other interfaces. It's currently down, so you need to turn it up. Use the IP link set dev up command to bring it up. Now for the namespaces, this interface is like a switch that it can connect to. So think of it as an interface for the host and a switch for the namespaces. So the next step is to connect the namespaces to this new virtual network switch. Earlier, we created the cable or the ETH pair with the vETH red interface on one end and blue interface on the other because we wanted to connect the 2 namespaces directly. Now, we will be connecting all namespaces to the bridge network. So we need new cables for that purpose. This cable doesn't make sense anymore, so we will get rid of it. Use the IP link delete command to delete the cable. When you delete the link with one end, the other end gets deleted automatically since they are a pair. Let us now create new cables to connect the namespaces to the bridge. Run the IP link add command and create a pair with vETH red on one end like before, but this time the other end will be named vETH red BR as it connects to the bridge network. This naming convention will help us easily identify the interfaces that associate to the red namespace. Similarly, create a cable to connect the blue namespace to the bridge network. Now that we have the cables ready, it's time to get them connected to the namespaces. To attach one end of the interface to the red namespace, run the IP link set vETH red netns red command. To attach the other end to the bridge network, run the IP link set command on the vETH red BR end and specify the master for it as the vnet0 network. Follow the same procedure to attach the blue cable to the blue namespace and the bridge network. Let us now set IP addresses for these links and turn them up. We will use the same IP addresses that we used before, 192.168.15.1 and 192.168.15.2. And finally, turn the devices up. The containers can now reach each other over the network. So we follow the same procedure to connect the remaining 2 namespaces to the same network. We now have all 4 namespaces connected to our internal bridge network, and they can all communicate with each other. They have all IP addresses 192.168.15.1, 2, 3, and 4. And remember, we assigned our host the IP 192.168.1.2. From my host, what if I tried to reach one of these interfaces in these namespaces? Would it work? No, my host is on one network and the namespaces are on another. But what if I really want to establish connectivity between my host and these namespaces? Remember, we said that the bridge switch is actually a network interface for the host. So we do have an interface on the 192.168.15 network on our host. Since it's just another interface, all we need to do is assign an IP address to it so we can reach the namespaces through it. Run the ipaddr command to set the IP 192.168.15.5 to this interface. We can now ping the red namespace from our local host. Now remember, this entire network is still private and restricted within the host. From within the namespaces, you can't reach the outside world, nor can anyone from the outside world reach the services or applications hosted inside. The only door to the outside world is the Ethernet port on the host. So how do we configure this bridge to reach the LAN network through the Ethernet port? Say there is another host attached to our LAN network with the address 192.168.1.3. How can I reach this host from within my namespaces? What happens if I try to ping this host from my blue namespace? The blue namespace sees that I'm trying to reach a network at 192.168.1, which is different from my current network of 192.168.15. So it looks at its routing table to see how to find that network. The routing table has no information about other network, so it comes back saying that the network is unreachable. So we need to add an entry into the routing table to provide a gateway or door to the outside world. So how do we find that gateway? A door or a gateway, as we discussed before, is a system on the local network that connects to the other network. So what is a system that has one interface on the network local to the blue namespace, which is the 192.168.15 network, and is also connected to the outside LAN network? Here's a logical view. It's the local hosts that have all these namespaces on, so you can ping the namespaces. Remember, our local host has an interface to attach to the private network, so you can ping the namespaces. So our local host is the gateway that connects the two networks together. We can now add a route entry in the blue namespace to say route all traffic to the 192.168.1 network through the gateway at 192.168.15.5. Now, remember, our host has two IP addresses, one on the bridge network at 192.168.15.5 and another on the external network at 192.168.1.2. Can you use any in the root? No, because the blue namespace can only reach the gateway in its local network at 192.168.15.5. The default gateway should be reachable from your namespace when you add it to your route. When you try to ping now, you no longer get the network unreachable message, but you still don't get any response back from the ping. What might be the problem? We talked about a similar situation in one of our earlier lectures, where from our home network, we tried to reach the external internet through our router. Our home network has our internal private IP addresses that the destination network don't know about, so they cannot reach back. For this, we need NAT enabled on our host, acting as a gateway here, so that it can send the messages to the LAN in its own name with its own address. So how do we add NAT functionality to our host? You should do that using IP tables. Add a new rule in the NAT IP table in the post routing chain to masquerade or replace the from address on all packets coming from the source network 192.168.15.0 with its own IP address. That way, anyone receiving these packets outside the network will think that they're coming from the host and not from within the namespaces. When we try to ping now, we see that we are able to reach the outside world. Finally, say the LAN is connected to the internet. We want the namespaces to reach the internet. So we try to ping a server on the internet at 8.8.8.8 from the blue namespace. We receive a familiar message that the network is unreachable. By now we know why that is. We look at the routing table and see that we have routes to the network 192.168.1, but not to anything else. Since these namespaces can reach any network our host can reach, we can simply say that to reach any external network, talk to our host. So we add a default gateway specifying our host. We should now be able to reach the outside world from within these namespaces. Now, what about connectivity from the outside world to inside the namespaces? Say, for example, the blue namespace hosts a web application on port 80. As of now, the namespaces are on an internal private network and no one from the outside world knows about them. You can only access these from the host itself. If you try to ping the private IP of the namespace from another host on another network, you will see that it's not reachable. Obviously because that host doesn't know about this private network. In order to make that communication possible, you have two options. The two options that we saw in the previous lecture on NAT. The first is to give away the identity of the private network to the second host. So we basically add an IP route entry to the second host, telling the host that the network 192.168.15 can be reached through the host at 192.168.1.2. But we don't want to do that. The other option is to add a port forwarding rule using IP tables to say any traffic coming to port 80 on the local host is to be forwarded to port 80 on the IP assigned to the blue namespace. Well, that's it for this video. Thank you for watching. Hello and welcome to this lecture. In this lecture, we look at container networking interface. So far, we saw how network namespaces work, as in how to create an isolated network namespace environment within our system. We saw how to connect multiple such namespaces through a bridge network, how to create virtual cables or pipes with virtual interfaces on either end, and then how to attach each end to a namespace and the bridge. We then saw how to assign IP and bring them up, and finally enable NAT or IP masquerade for external communication, etc. We then saw how Docker did it for its bridge networking option. It was pretty much the same way, except that it uses different naming patterns. Well, other container solutions solve their networking challenges in kind of the same way, like Rocket or Mesos Containerizer, or any other solutions that work with containers and requires to configure networking between them, like Kubernetes. If we are all trying to solve the same networking challenges by researching and finally identifying a similar approach with our own little minor differences, why code and develop the same solution multiple times? Why not just create a single standard approach that everyone can follow? So we take all of these ideas from the different solutions and move all the networking portions of it into a single program or code. And since this is for the bridge network, we call it bridge. So we created a program or script that performs all the required tasks to get the container attached to a bridge network. For example, you could run this program using its name bridge and specify that you want to add this container to a particular network namespace. The bridge program takes care of the rest so that the container runtime environments are relieved of those tasks. For example, when Rocket or Kubernetes creates a new container, they call the bridge program and pass the container ID and namespace to get networking configured for that container. So what if you wanted to create such a program for yourself, maybe for a new networking type? If you were doing so, what arguments and commands should it support? How do you make sure the program you create will work correctly with these runtimes? How do you know that container runtimes like Kubernetes or Rocket will invoke your program correctly? That's where we need some standards defined. A standard that defines how a program should look, how container runtimes will invoke them so that everyone can adhere to a single set of standards and develop solutions that work across runtimes. That's where Container Network Interface comes in. The CNI is a set of standards that define how programs should be developed to solve networking challenges in a container runtime environments. The programs are referred to as plugins. In this case, Bridge program that we have been referring to is a plugin for CNI. CNI defines how the plugin should be developed and how container runtimes should invoke them. CNI defines a set of responsibilities for container runtimes and plugins. For container runtimes, CNI specifies that it is responsible for creating a network namespace for each container. It should then identify the networks the container must attach to. Container runtime must then invoke the plugin when a container is created using the add command, and also invoke the plugin when the container is deleted using the del command. It also specifies how to configure a network plugin on the container runtime environment using a JSON file. On the plugin side, it defines that the plugin should support add, del, and check command line arguments, and that these should accept parameters like container and network namespace. The plugin should take care of assigning IP addresses to the pods and any associated routes required for the containers to reach other containers in the network. At the end, the results should be specified in a particular format. As long as the container runtimes and plugins adhere to these standards, they can all live together in harmony. Any runtime should be able to work with any plugin. CNI comes with a set of supported plugins already, such as Bridge, VLAN, IPVLAN, MacVLAN, one for Windows, as well as IPAM plugins like Host Local and DHCP. There are other plugins available from third-party organizations as well. Some examples are Weave, Flannel, Cilium, VMware NSX, Calico, Infoblox, etc. All of these container runtimes implement CNI standards, so any of them can work with any of these plugins. But there is one that is not in this list. Docker. Docker does not implement CNI. Docker has its own set of standards known as CNM, which stands for Container Network Model, which is another standard that aims at solving container networking challenges similar to CNI but with some differences. Due to the differences, these plugins don't natively integrate with Docker, meaning you can't run a Docker container and specify the network plugin to use a CNI and specify one of these plugins. But that doesn't mean you can't use Docker with CNI at all. You just have to work around it yourself. For example, create a Docker container without any network configuration, and then manually invoke the Bridge plugin yourself. That is pretty much how Kubernetes does it. When Kubernetes creates Docker containers, it creates them on the none network. It then invokes the configured CNI plugins who take care of the rest of the configuration. We talk about CNI. Hello and welcome to this lecture. In this lecture, we look at the networking configurations required on the master and worker nodes in a Kubernetes cluster. The Kubernetes cluster consists of master and worker nodes. Each node must have at least one interface connected to a network. Each interface must have an address configured. The hosts must have a unique host name set, as well as a unique MAC address. You should note this especially if you created the VMs by cloning from existing ones. There are some ports that needs to be opened as well. These are used by the various components in the control plane. The master should accept connections on 6443 for the API server. The worker nodes, Kube Control Tool, external users, and all other control plane components access the Kube API server via this port. The kubelets on the master and worker nodes listen on port 10250. Yes, in case we didn't discuss this, the kubelets can be present on the master node as well. The kube scheduler requires port 10251 to be open. The kube controller manager requires port 10252 to be open. The worker nodes expose services for external access on ports 30,000 to 32,767. So these should be open as well. Finally, the HCD server listens on port 2379. If you have multiple master nodes, all of these ports need to be open on those as well. And you also need an additional port 2380 open so the HCD clients can communicate with each other. The list of ports to be opened are also available in the Kubernetes documentation page. So consider these when you set up networking for your nodes in your firewalls or IP table rules or network security group in a cloud environment such as GCP or Azure or AWS. And if things are not working, this is one place to look for while you're investigating. Head over to the practice session and explore the networking setup in the existing environment. Keep these commands handy while you look for information. We will start with simple exercises where you will explore an existing Kubernetes cluster and view information about the interfaces, IPs, hostnames, ports, etc. This will help you familiarize with the environment and look for information in the future sections. Going forward, we will get into more challenging exercises. For now, let's start slow.
For the first question is asking us how many nodes are part of this cluster. So node for under control plane, we can see it's here. I'm going to run the command. So there's two commands. You can either do IP address or you can do IP link. It doesn't matter which one you use. Each one will give you the same information. So we do IP address, and what you want to do is find the interface that has this specific IP. So we will go down and we'll see 114.3. And if you go through all the interfaces, when we get down to Ethernet 0, we can see that it's got the 114.3. So this IP address is bound to this interface. So this is what's going to be used for cluster connectivity. So I'll select Ethernet 0. Now it's asking for what is the MAC address of the interface on the control plane. So it's asking us what's the MAC address of the interface of Ethernet 0. So we're already here. We've already got the output open. So we can just run this right here. So this is the answer, 7203. It's going to be this guy. But if you wanted to, you could also run IP address show and then the name of the interface. So if you just wanted to see the information for this interface without it cluttering your screen, you could do show Ethernet 0, and that's going to give us all of the same information, but just for this interface. Now it's asking us what is the IP address assigned to node 1. So we'll do kubectl get nodes -o wide. And now we grab the internal IP of node 1, which is the 114.6. So I'll grab, that's this guy right here. And so I'll grab 114.6. What is the MAC address assigned to node 1? So we're going to do the same steps for node 1. I'm going to SSH to that one first. So now we're on node 1, and I can just do an IP address. And we got to look for the 114.6. So if I scroll down, we can see 114.6. That's also Ethernet 0 on node 1. And then if you take a look at the MAC address for that interface, we can see it's 7206. So I'll select 7206. The next question is asking us, we use the container D as a container runtime. What is the interface bridge created by on that host? So this is asking specifically, back on the control plane, we'll do IP address or IP link. And we want to look for the bridge interface that the container D is going to be using. So that's going to be the CNI 0. Now, I know that's what's going to be the bridge interface, but if you didn't know that that was a bridge interface on a Linux host, what you can do is you can run this command IP address show. So this is going to show you, based off of certain criteria, what interfaces you're interested in. And you type in type and bridge. So this is going to show you all of the bridge interfaces on this machine. And so here you can see the only bridge interface is CNI 0. So we'll select CNI 0. What is the state of interface CNI 0? So we've already got this information up. If you just scroll to the right, you should see a state of up right here. The next question is asking us, if you were to ping Google from the control plane node, what route does it take? Basically, it's asking us what is the IP address of the default gateway. So I'm going to do a IP route. This is going to list all of the routes on this host. And we could see that the default route is via 172.25.01 on Ethernet 1 interface. So that's the IP address of the default gateway, 172.25.01. So basically, anytime you send a request to anybody that's outside of any of the following networks, which you already have routes for, it's by default going to go to this IP address right here. The next question is asking us, what is the port the kube scheduler is listening on in the control plane? So to figure out what port it's listening on, we're going to want to use the netstat command. And I recommend you take a look at the different flags so we can figure out what we want. And I realize that there's a typo. Okay, so we do netstat. Now, a couple of things that we want, since we want to figure out what port it's listening on, we want the -L. This is going to be display listening server sockets. Also, I want to be able to do, like a netstat and then filter based off of, scheduler to figure out the schedule process. So we want to do the -P flag, which is going to list out the program name so that we can actually grep for the scheduler. And then finally, the other flag that I usually like to do in general, which is the -N flag here, which is saying don't resolve the names of the ports. Right? Don't resolve the names of the ports or the IP addresses. I want to be able to physically see the number, or then it's going to try to figure out what is the protocol that uses that specific port. So let's run those flags. I'll do -NPL, and then I'm going to do a pipe grep.
Hello and welcome to this lecture. In this lecture, we discuss about pod networking in Kubernetes. So far, we have set up several Kubernetes master and worker nodes and configured networking between them so they are all on a network that can reach each other. We also made sure the firewall and network security groups are configured correctly to allow for the Kubernetes control plane components to reach each other. Assume that we have also set up all the Kubernetes control plane components, such as the kubeAPI server, the etcd servers, kubelets, etc., and we're finally ready to deploy our applications. But before we can do that, there is something that we must address. We talked about the network that connects the nodes together, but there's also another layer of networking that is crucial to the cluster's functioning, and that is the networking at the pod layer. Our Kubernetes cluster is soon going to have a large number of pods and services running on it. How are the pods addressed? How do they communicate with each other? How do you access the services running on these pods internally from within the cluster, as well as externally from outside the cluster? These are challenges that Kubernetes expects you to solve. As of today, Kubernetes does not come with a built-in solution for this. It expects you to implement a networking solution that solves these challenges. However, Kubernetes have laid out clearly the requirements for pod networking. Let's take a look at what they are. Kubernetes expects every pod to get its own unique IP address, and that every pod should be able to reach every other pod within the same node using that IP address. And every pod should be able to reach every other pod on other nodes as well, using the same IP address. It doesn't care what IP address that is and what range or subnet it belongs to. As long as you can implement a solution that takes care of automatically assigning IP addresses and establish connectivity between the pods in a node as well as pods on different nodes, you're good, without having to configure any NAT rules. So how do you implement a model that solves these requirements? Now, there are many networking solutions available out there that does these. But we've already learned about networking concepts, routing, IP address management, namespaces, and CNI. So let's try to use that knowledge to solve this problem by ourselves first. This will help in understanding how other solutions work. I know there is a bit of repetition, but I'm trying to relate the same concept and approach all the way from plain network namespaces on Linux all the way to Kubernetes. So we have a 3-node cluster. It doesn't matter which one is master or worker, they all run pods either for management or workload purposes. As far as networking is concerned, we're going to consider all of them as the same. So first, let's plan what we're going to do. The nodes are part of an external network and has IP addresses in the 192.168.1. series. Node 1 is assigned 11, node 2 is 12, and node 3 is 13. Next step, when containers are created, Kubernetes creates network namespaces for them. To enable communication between them, we attach these namespaces to a network. But what network? We've learned about bridge networks that can be created within nodes to attach namespaces. So we create a bridge network on each node and then bring them up. It's time to assign an IP address to the bridge interfaces or networks. But what IP address? We decide that each bridge network will be on its own subnet. Choose any private address range, say 10.244.1, 10.244.2, and 10.244.3. Next, we set the IP address for the bridge interface. So we have built our base. The remaining steps are to be performed for each container and every time a new container is created. So we write a script for it. Now, you don't have to know any kind of complicated scripting. It's just a file that has all commands we will be using. And we can run this multiple times for each container going forward. To attach a container to the network, we need a pipe or a virtual network cable. We create that using the IP-link add command. Don't focus on the options as they are similar to what we saw in our previous lectures. Assume that they vary depending on the inputs. We then attach one end to the container and another end to the bridge using the IP-link set command. We then assign IP address using the IP-addr command and add a route to the default gateway. But what IP do we add? We either manage that ourselves or store that information in some kind of database. For now, we will assume it is 10.244.1.2, which is a free IP in the subnet. We discuss about IP address management in detail in one of the upcoming lectures. Finally, we bring up the interface. We then run the same script, this time for the second container with its information and gets the container connected to the network. The two containers can now communicate with each other. We copy the script to the other nodes and run the script on them to assign IP address and connect those containers to their own internal networks. So we have solved the first part of the challenge. The pods all get their own unique IP address and are able to communicate with each other on their own nodes. The next part is to enable them to reach other pods on other nodes. Say, for example, the pod at 10.244.1.2 on node 1 wants to ping pod 10.244.2.2 on node 2. As of now, the first has no idea where the address 10.244.2.2 is because it is on a different network than its own. So it routes to node 1's IP as it is set to be the default gateway. Node 1 doesn't know either since 10.244.2.2 is a private network on node 2. Add a route to node 1's routing table to route traffic to 10.244.2.2 via the second node's IP at 192.168.1.12. Once the route is added, the blue pod is able to ping across. Similarly, we configure route on all hosts to all the other hosts with information regarding the respective networks within them. Now, this works fine in this simple setup. But this will require a lot more configuration as and when your underlying network architecture gets complicated. Instead of having to configure routes on each server, a better solution is to do that on a router if you have one in your network and point all hosts to use that as the default gateway. That way you can easily manage routes to all networks in the routing table on the router. With that, the individual virtual networks we created with the address 10.244.1.0/24 on each node now form a single large network with the address 10.244.0.0/16. It's time to tie everything together. We performed a number of manual steps to get the environment ready with the bridge networks and routing tables. We then wrote a script that can be run for each container that performs the necessary steps required to connect each container to the network. And we executed the script manually. Of course, we don't want to do that, as in large environments where thousands of pods are created every minute. So how do we run the script automatically when a pod is created on Kubernetes? That's where CNI comes in, acting as the middleman. CNI tells Kubernetes that this is how you should call a script as soon as you create a container. And CNI tells us this is how your script should look like. So we need to modify the script a little bit to meet CNI standards. It should have an add section that will take care of adding a container to the network, and a delete section that will take care of deleting container interfaces from the network and freeing the IP address, etc. So our script is ready. The kubelet on each node is responsible for creating containers. Whenever a container is created, the kubelet looks at the CNI configuration passed as a command line argument when it was run and identifies our script's name. It then looks in the CNI's bin directory to find our script and then executes the script with the add command and the name and namespace ID of the container. And then our script takes care of the rest. We will look at how and where the CNI is configured in Kubernetes in the next lecture along with practice tests. For now, that's it from the Pod Networking Concepts lecture. Hopefully that should give you enough. Hello and welcome to this lecture. In this lecture, we will discuss about CNI in Kubernetes. In the prerequisite lectures, we started all the way from the absolute basics of network namespaces. Then we saw how it is done in Docker. We then discussed why you need standards for networking containers and how the container network interface came to be. And then we saw a list of supported plugins available with CNI. In this lecture, we will see how Kubernetes is configured to use these network plugins. As we discussed in the prerequisite lecture, CNI defines the responsibilities of container runtime. As per CNI, container runtimes, in our case Kubernetes, is responsible for creating container network namespaces, identifying and attaching those namespaces to the right network by calling the right network plugin. So where do we specify the CNI plugins for Kubernetes to use? The CNI plugin must be invoked by the component within Kubernetes that is responsible for creating containers, because that component must then invoke the appropriate network plugin after the container is created. The CNI plugin is configured in the kubelet service on each node in the cluster. If you look at the kubelet service file, you will see an option called network plugin set to CNI. You can see the same information on viewing the running kubelet service. You can see the network plugin set to CNI and a few other options related to CNI, such as the CNI bin directory and the CNI config directory. The CNI bin directory has all the supported CNI plugins as executables, such as the bridge, DHCP, flannel, etc. The CNI config directory has a set of configuration files. This is where kubelet looks to find out which plugin needs to be used. In this case, it finds the bridge configuration file. If there are multiple files here, it will choose the one in alphabetical order. If you look at the bridge conf file, it looks like this. This is a format defined by the CNI standard for a plugin configuration file. Its name is mynet, type is bridge. It also has a set of other configurations which can be related to the concepts we discussed in the prerequisite lectures on bridging, routing, and masquerading in NAT. The EAST gateway defines whether the bridge network should get an IP address assigned to it so that it can act as a gateway. The IP masquerade defines if a NAT rule should be added for IP masquerading. The IPAM section defines IPAM configuration. This is where you specify the subnet or the range of IP addresses that will be assigned to pods and any necessary routes. The type host local indicates that the IP addresses are managed locally on this host, unlike DHCP server maintaining it remotely. The type can also be set to DHCP to configure an external DHCP server. Well, that's it for this lecture. Head over to the practice exercises and practice working with CNI in Kubernetes.